Hi, everyone. So I don't know if you know me, but I'm coming from the direct imaging community. So this is why you're not seeing a free-floating planetary mass object here, but just more of an artistic, probably generated by AI view of two planets which are accreting material from their circumplanetary disk. But what really matters is to understand the physics of these two classes of objects and the accretions that is occurring. Is it different between the two classes of objects, or is it driven by a single phenomenon? And to do so, the initial motives of what I will be presenting today on my side have been the discovery of protoplanets. So this happened in 2018 with the discovery of PDS-70b and C. You probably have seen the image of these two baby planets carving the material through the disk around a solar-type star. Here, this is on the top, you have an image of a more recently discovered protoplanets. This is Speed 2b. It's probably a few Jupiter mass only. And as you see, it's just eating the material within the dust distribution around the disk. So you have a disk with a structured dust distribution with many rings. And you see that you have this point source here. This is the planet, the protoplanet. And what is fascinating is that this protoplanet has been also detected using H-alpha filters, which means that it is emitting H-alpha and it is actually actively accreting materials from the disk, from the gas in this disk that you actually don't see in this image. So the discovery of these objects have been triggering a lot of theoretical developments, trying to understand in more details how these objects were accreting the gas from the circumstellar disks. So as it has been said, today we think that materials should flow from the circumstellar disk up to the planet. The way it's channeling to the planet is not fully clear yet. It could fall at the surface of the disk surrounding the planet, the circumplanetary disk, creating a shock. The shock is going to emit, so it might be responsible for the emission line I was mentioning emitted by the planet. The other hypothesis is that the material is being accreting directly at the pole at high latitude onto the planet. And there is one remaining fundamental question is whether the planet, which is young, partly convective, with an interior that is also partly ionized, could power magnetic fields that are strong enough to trigger what we know on classical T-Tauri stars, which is magnetospheric accretion, where the magnetic field is going to truncate the circumplanetary disk and will lift material from the circumplanetary disk along the planet magnetic field lines up to the planet's surface, and it will create a very localized accretion shock where the line emission of the planet will be produced. And this is the question today I'm going to try to investigate, is whether this mechanism is operating both on companions and on a free-floating object. To do so, we tried to, so I'm an observer, so we tried to identify diagnostics that had been used for identifying magnetospheric accretions on stars. And there is two that are interesting in our case, which can be reapplied on planetary mass objects. One is the study of the variability of the emission line. So variability in the emission line is something ubiquitous in the stellar mass regime, and we could expect it to be also present in the planetary mass range. And if you study the amplitude and the timescale of variability, well, you can find patterns that are very typical of magnetospheric accretion. You can also try to analyze the line at high spectral resolution. If you do so, you will have access to the kinematic of the infalling material onto your planetary mass object. And if you look at the evolution of the line profile in time, models also predict that you should see specific patterns within the profile that can only be produced by magnetospheric accretion. So this is what motivated us to conduct a survey with UVES at VLT. So UVES is an echelle spectrograph. It's operating in the optical, and it has no adaptive optics. So you can only rely on the good seeing conditions to look at your object and have a good SNR on your data. We were a bit crazy. We thought that we might want to point it to some systems where you have a star and a companion, which is at a few arc seconds away from the star. And so we tried that, and in fact, it worked. Under relatively good seeing conditions, you can orientate the entrance slit of the instruments on the star and on the companion. And you can actually see the H-alpha emission from the companion that you see is distinct from the one of the star. And using a custom algorithm along the slit, you can deblend basically the H-alpha line from the companion from the one of the star and study its line profile. You can do this for other lines because the instrument is covering the whole optical range up to the UV. And so you can access other emission lines. For instance, this is H beta. And so this is what we did. We did that on actually on many other objects now. We got awarded a large program on UVES of about, in total, around 200 hours of telescope time. And the goal of this program is to understand what are the line profiles of these planetary mass objects, whether they are bound or free-floating. How do they evolve for objects with different ages, different masses, and how do they evolve in time? So we're investigating the variability, in particular, the one on the relatively short time scale of a few consecutive days to map basically possible modulations of the line profile induced by the rotation of the object to evidence the funnel flows getting in and out of the field of view as the object is rotating. And so today the survey is running, so I can show you some snapshot results. Here is what we're seeing on 6 consecutive nights on 6 Jupiter mass objects, which is free-floating. This is H-alpha, so you have the line profile, and you can see that we're seeing really a crazy behavior from one line to the next. The line can have varied in shape, and even from one exposure to the next in 30 minutes. You can see noticeable differences in the line profile, showing that all these objects are variable. They have a complex behavior. This is another example on this time on a bound companion. We got excellent sync condition, 0.5 sync during 3 hours. So we decided to look at a companion, which is a WISES 1b. It's a 14 Jupiter mass companion around a J-type star. It's located at 1.7 arc seconds, and we could get the H-alpha line profile of this object. We also got helium line profile of that object, which trace directly the emission at the accretion shock of the planet. And just to give you a kind of a summary of where we are now. So the survey is almost completed. We have one run left that will be conducted in the spring of next year. Here's kind of the diversity we are seeing. So we are seeing a lot of diversity. And so on some objects, and this is an example here. This is a 45 million years old object. It still has a disk with a significant excess emission. And you can see that here we observed it in January. You see that the profile was extremely broad, extremely variable. This is just several exposures on the objects taken consecutively. So you can see that the variation is incredible. And this is what we were seeing like in October of this year. So a few months, 10 months later, basically. So this time the profile was very narrow. The line was weak. So we were probably seeing this October the system in quiescence, and probably some profile more typical of chromospheric activity here. So we're seeing a lot of diversity, but let's focus now on one object that I'd like to mention, because this is where the analysis is more mature, and we have learned a lot from that object. So it's the LORM 1ABB. It's 13 Jupiter mass objects around a pair of 45 million years old star. The object, the companion, is known to have a disk. It was found with the James Webb Space Telescope. So the disk has MIRI-MRS spectroscopy. It's showing gas emission filter. So it has gas, basically. It has also dust, of course. And so the object was known for a long time to be accreting. So we collected 32 epochs with UVES. The coverage is covering about two years of time span on the emission line. With UVES, so you can, on this object, we could actually collect a mean spectrum. You can see that we can detect the UV excess on that object. We can see the UV excess varying in time. So this is tracing directly the accretion shock at the surface of the companion. And we see this series of hydrogen emission line. We see a helium line that I will also talk about a bit later on. And we see some metallic lines, which are here, actually, they are faint, but they appear in the outburst phase of the object. And these lines on T-Tauri stars, where their origin is still debated, but they might be forming into the funnel flows in T-Tauri stars. So let's focus on the hydrogen line. This is what we're getting. So we're getting this time series of profile at a high signal-to-noise ratio. We are able to see several Balmer lines. And you see that the Balmer lines don't have necessarily the same profile. What we will be focusing on is these first three lines, which have the most exquisite signal-to-noise ratio. And if you look at this line, actually, well, the first thing we thought was to decompose the line profile using Gaussians, because this is something that is usually done with T-Tauri stars. And that's the most basic hypothesis you can do on the line components forming the whole line profile and explain the variability. But in fact, when you look at protoplanet accretion models and models for accretion of free-floating planets, there is no reason why accretion mechanisms should produce Gaussians, basically line profiles. So we decided to explore other possible decomposition, and what we found out is that using algorithm similar to principal component analysis, we could find within the series of line profile, two components, so two possible components explaining the whole variability of the lines. One that is the green component, the core component, which is very narrow. This component, it's possibly caused by chromospheric activity that you would expect to be relatively strong on this kind of young objects. And the blue component, this broader component, the wing component, this one is very much more typical of magnetospheric accretion. And this one is modulating the shape of the profile, while the core component, the narrow component, is modulating the intensity. This decomposition, we are retrieving it independently for every Balmer lines. So this is really something, this is really a pattern that is truly there within the data, that is truly there within the line structure. And we try to model it with protoplanet accretion models. So on the left, you have a fit of the wing component, the broad component, with models that have been designed for PDS 70B and C. And you can see that basically to the first order, we can reproduce these absorptions at 0 kilometers per second only by magnetospheric accretion models. While the core component, the narrow component, is better fitted with 1D shock models that have been created and for also studying PDS 70, and that might correspond to a shock either at the planet surface or on the circumplanetary disk. Concerning the variability, so that's the other diagnostic I was mentioning at the start of my talk. So we also try to recreate this diagnostic that has been proposed for T-Tauri stars. And the variability is actually the pattern, is also reminiscent of the one we're seeing on classical T-Tauri stars, which is another possible indication for magnetospheric accretion. Another set of lines that we studied are the helium line. So the helium line, usually people are studying the helium triplets, at 1.08 micron because it is relatively bright above the continuum. In our case, actually, the setup we choose with UVES, we had to make a trade-off, and we had to cut before the triplets. So but fortunately, on the LORM, you can see a series of helium lines in the optical. And what is interesting is that these helium lines, some are emitted from the same upper level. So you can also model basically the line emission and try to get some insights on the physical conditions of producing of the gas that is responsible for the line emission. And what we are finding is that for two of the lines, they can only be produced with the properties we see if we consider high density and an emission near the thermal equilibrium. And typically, this is what we would expect if they were formed at the accretion shock at the surface of the object. We also see that these lines are correlated with the UV excess. That is another indication that we're seeing the accretion shock through these lines. And we also see narrow and broad component. This is something that was already seen on T-Tauri stars for these lines. And you really need to have this high resolution, 50,000 to really study these lines, because otherwise, I mean, they are very narrow, and you would just miss the important information. Okay, so I will just give you a few takeaway messages. So the survey is still ongoing. We are collecting more and more data. We are very lucky with the weather at the VLT, actually. But what we are seeing is that the emissions on planetary mass objects, they are ubiquitous when you have a IAR access. You just have to wait, and at some point they will pop up. So that's one important thing that we are getting, one important feedback. There are all the objects, once they have a line, it's variable, and they have very diverse properties. And on the LOM, as I can say, there is a kind of different insights pointing towards magnetospheric accretion. We still need to be careful, of course, but still, this is probably one of the set of data where we have this from the different angle. We can try to be convinced that magnetospheric accretion is one of the driving mechanisms. The survey has been producing several papers. I encourage you to take a look. And the other important message I wanted to share with you is that this is the survey and entropy in general. This is an open international collaboration. So if you want, you're interested to contribute or to just be interested to please reach out. I think we have we are building kind of a community around that topic, and so adding data or completing existing data on your favorite objects, this is something we could do with the last run that we have, or with the data that we have in hand already. Thank you for your attention.
Thank you. Hi, I'm confused about the physical intuition for the two components. When I think of magnetospheric accretion, it makes me think accretion along the magnetic field lines and then a shock, but it's separate from the shock. So how should I be thinking about it?
Yeah, I don't know. I think the physical interpretation, especially of the core component, I don't think we have the pure answer right now. It can be fitted by shock model, so it could indeed be formed at the accretion shock on the planet. So we could be seeing actually what we believe from also the helium line at the moment, that we're probably seeing part of the emission that is in the funnel flow and part of the emission that is very close to the shock. Yeah. So whether this is created at the shock, or whether this is something else like chromospheric activity, more boring, but this could be this as well. Well, we will need to look at the other objects in the survey to have a more comprehensive understanding of what it could be actually. Yeah.
Hey, Mickael, great talk. Actually, I have two questions. The first one would be if you measure the accretion mass rates and if you compare it with others. And the second would be why an object like the long one ABB being 45 million years old, why is it still accreting?
Yeah, that's an open question. I think we don't have the knowledge yet when the accretion is stopping on those objects. What I can tell is that on M dwarfs, there are still disks around objects of 50 million years. So it's possible that accretion could actually happen even at a later age than 50 million years on the planetary mass range. This is an open question. And to answer your question on the accretion rate, so actually the LOM is accreting at an accretion rate which is similar to the one of PDSM and TBNC. So that's thrilling. Yeah. At least during the accretion burst that we are seeing at some point in the data. Yeah.
Hey, Mickael, here.
Great talk, Mickael. I was curious about the UV excess, how much you've done with it, and whether you can use sort of accretion rate constraints derived from that with I guess a slab model or something against what you derive from the lines to kind of start to think about kind of cross checks and calibrating these relations.
Yeah, so this is what we did actually. We contacted Carlo Manara from ISO, and he has a slab model. So we fitted the slab at different epochs, compared it to the lines. So this was very interesting actually. So we find a very tight correlation between the wing components, the flux of these wing components, and the UV excess. That's not so much the case for the green components. So that's arguing towards chromospheric activity in my sense. But yes, we can also calibrate. What we're finding, there is a shift I don't remember. I think it's, I will check in the paper, but we can discuss this later. I think it's an order of magnitudes between the two accretion rates, the one you derive from the slab and the one you derive from the alkali-metal relations on the lines. So, well, but this is something that was already, in the air, basically, so.
4 years ago, my first edit.
Yeah, I wanted to say thank you because this is, yeah, and I wanted to, yeah, and I wanted to say thank you because all this pioneering work that you have been doing, I think work sometimes comparing your lines profile from 20 years ago to the one of the object, and it's funny. So last question.
Mickael, yeah.
Yes.
Do you also see some forbidden lines like oxygen 1 or sulfur 2 associated to jets? No, no jets.
Okay. Not yet, at least not yet.
All right.
Great. Then I think in the interest of coffee and croissants, let's thank the speaker again.